One of the things that we need to look at is the potential for natural forcings to affect climate change. We hear in the media a lot and the news, and also it's something that we do need to study about the human impact on our climate. The fact that obviously our release of carbon dioxide and other greenhouse gases is causing an anthropogenic or human-induced climate change. However, what is important to realise is it's not the only thing that's affected climate. Climate has been changing long before humans had a major interference with it. And we can use proxy data from ice cores and tree rings, which is something another video we'll look at, to determine this. And one of the things that we know affects climate is orbital variations in the Earth's kind of movement around the sun. The theory of this was proposed by Milankovitch, and the theory has been known now as the Milankovitch Cycles. And there's three kind of elements of this. Firstly, we need to consider the eccentricity of the Earth's orbit. Now, we kind of assume that the Earth orbits around the Sun in a circular fashion. The problem is when we look at it from space, that's kind of what it looks like, because anything to sort of judge the shape of the orbit is such a long distance away that we basically see it as a circle. But this isn't actually always the case. Every 100,000 years or so, the Earth's orbit changes in shape from what we call high eccentricity to low eccentricity. Okay. Our diagram shows that here. The orbit around the Sun, shown by the orange circle, in orbit A, is low eccentricity. It's virtually circular. This means that at pretty much any point around the orbit of the Earth, also the orbit of the Sun, the Earth is at a sort of similar distance from the Sun. B shows a high eccentricity orbit. Okay, it's more elliptical in shape, so we have a point at which the Earth may be very close to the Sun, and then also points at which it's much further away. Okay, now the point that is when the Earth is closest to the Sun is known as the perihelion. Okay, obviously, when we have an highly eccentric orbit, that elliptical shape, the perihelion is actually much closer to the Sun than at any point during that low eccentricity or circular orbit. But obviously at the same time, the aphelion, which is the point at which the Earth is further away from the Sun, is much further away in that eccentric orbit than it ever would be in that low eccentricity or circular orbit. What this does is have major impacts on the seasonal changes in temperatures. Okay? When the Earth is at its perihelion, it's obviously, particularly in the high eccentricity orbit, it's going to be receiving a high amount of solar energy and therefore going to be receiving quite warm temperatures. However, when it reaches that low, that aphelion, where it's very far away from the Sun, because obviously in this case, in the high eccentricity orbit, it's much further away, it's going to receive a lot less solar energy and therefore temperatures are going to be much colder. The second element of the Milankovitch cycles refers to a term called obliquity. Okay? Now, obliquity basically changes every 40,000 years, and it basically refers to the tilt of the Earth's axis. Okay? Currently, the Earth is actually tilted away from a straight axis by about 22.5 to 23.5 degrees. Okay? Now, that axis or that tilt will actually vary between 22 degrees to 24.5 degrees tilt. Now that doesn't seem a huge amount, but it does have quite significant impacts. The more the Earth is tilted, so the higher that angle of tilt, so more towards the 24.5, 25 degrees angle of tilt, okay, the more severe the seasons will be. So what we mean by that is you'll have much more warm or quite hot summers, but also very severe and cold winters. The smaller the tilt, the less severe the seasonal changes. This means that winters will be milder and summers will be cooler. Now, it's thought that when the tilt is low, those cooler summers will allow ice to survive the summers, particularly in areas of high latitude, which over time will lead to the build-up of ice sheets and can lead to the development of ice ages, because you get this positive multiplier effect back. As soon as ice sheets start to form and can survive the winter, we increase the reflectivity of the Earth's surface. That means that sun's energy that's hitting the surface is hitting this highly reflective white or ice sheets and is reflected back out into space, helping temperatures drop. The final part of the Milankovitch cycles refers to a term called precession. Now, precession changes roughly every 19 to 26,000 years. So I put 23,000 there, that's kind of the middle point. Precession basically refers to the wobble of the Earth's axis. So basically we talked earlier when we talked about obliquity, about the Earth being on an axis that isn't necessarily straight at an angle of 23.5 degrees. But even sitting on that axis, it can wobble or move slightly from that central position. Now, as a result of that, the North Pole basically takes like a circular pattern, a bit like kind of a spinning top as it starts to wobble. And as a result of that, the position of the North Pole in terms of how it faces towards the sun can change. So at points of extreme wobble, it may face much closer to the sun than it normally would, or much further away. Now this can have significant impacts because it can change how much sunlight each hemisphere receives. So for example, if the northern hemisphere, if the wobble means that the North Pole faces away from the sun, it's obviously going to reduce the amount of sunlight the northern hemisphere receives whilst increasing the amount the southern hemisphere receives. It can also affect when seasons occur, so winter may start later or earlier than normal, and it also affects how severe these seasons are. Now, finally, we do also have to consider some other things that move away from orbital changes of the Milankovitch cycles in terms of affecting climate. Okay? And what we need to look at is two other factors. Okay, these are actually relatively simple. Okay, the first thing we need to consider are the idea of sunspots. Okay, now the sunspots, you can actually see them on the surface of the Earth. They normally show up as slightly darker patches on the surface of the sun. Okay? And we get clusters of these forming on the surface of the sun roughly every 11,000 years. Now the sunspots are actually caused by reductions in the surface temperature of the sun. When we get large clusters of these sunspots, it can actually result in a significant decrease in solar energy coming from the sun and being received by the Earth, resulting in cooler temperatures. One of the other major things that can affect climate is volcanic activity. Interestingly, volcanic activity can both have a warming and cooling effect on the Earth. For example, historically we know about things such as the Deccan Traps, or now known as the Deccan Plateau in India, which were a large area of really large volcanoes that had constant eruptions. And as I said, that had both cooling and warming impacts on the Earth's climate. We sometimes hear about volcanic activity causing global dimming. This is where things like ash and sulfur dioxide ejected by the volcano into the atmosphere act to reflect the solar energy back out into the atmosphere before it reaches the Earth's surface. If we take, for example, the Mount Pinatubo eruption in 1991, the amount of ash and sulfur dioxide emitted into the atmosphere actually resulted for that year in a 0.5 degree Celsius cooling of temperatures as solar energy was reflected back out to space. There's also historical circumstances where this has happened, where maybe more serious volcanoes or larger volcanoes than Mount Pinatubo erupted, and even some historians suggest that things, for example, at the Dark Ages may actually be due to a large amount of ash being ejected into the atmosphere by a supervolcano eruption. At the same time though, volcanic eruptions can cause global warming or kind of contribute to the warming of the atmosphere. The ejection of greenhouse gases such as carbon dioxide act to basically retain some of the long-wave radiation that tries to leave Earth. So as solar radiation comes in, it comes in as short-wave radiation, and then it's absorbed by the Earth's surface and then slowly released back into the atmosphere as long-wave radiation. And what greenhouse gases do is they basically act like a bit of a blanket. They keep that long-wave radiation in the Earth's atmosphere and stop it escaping. So volcanic activity can both cause a warming and a cooling.